Miss Kelly. This is going to be my video on the exam number 1 for my honors contract. So I'm going to be comparing calculus cross products to physics cross products. So first of all, the notation is a little bit different. So for vectors in Calc 3, we just use like the vector notation brackets. For physics, the same vector denoted by vector arrow always, because we're dealing with scalars and vectors in physics, so vector arrow is important. And then we don't usually use parentheses, but I like to use parentheses sometimes when we have units, so I don't have to write the unit each time over and over. So for example, say this is a vector of position of particle u, right? So we would say 1 I hat, 2 j hat, 3 k hat meters. Normally, if we didn't put the parentheses, you distribute it, you treat it as if it were, oh sorry, these are all pluses. So here you use commas, here you add them, because each component is its own thing, because in physics, they love their components. So like say you have a triangle, and this is your u vector, you have your u of x, just all in I hat direction, and your u of y, all in j hat direction. And they're treated as separate vectors sometimes when you need them to. So that's just like the main deal about physics. Now, when we're talking about the cross product, one of the applications for a physics cross product is a Lorenz force, denoted by F of B is equal to Q V cross B. So this is the Lorenz force. This is the magnetic force experienced by a moving particle in a magnetic field. Q is a charge of the particle, V is the velocity of the particle, and B is the external magnetic field. Now, this force is equal to mass times acceleration, right? Now, the way these particles work and move is that they take advantage of the orthogonal property of the cross product. So we know that if one vector points in this direction and the other one goes in this direction, the other one will point in this direction. That's just the way it goes. So we know that if a vector points this direction, let's say this is the velocity vector, and this is the magnetic field vector, your force will point out of the board into the screen. So let's do an example. I'm going to say that we're going to work with like a perfect case scenario. These are already 90 degrees angles because I want to prove something about the tangential and the normal acceleration. So we're just going to say that there's a particle with charge q and it has a mass, and it's moving in the I hat direction at 3 times 10 to the 10th meters per second. Velocity charge is equal to, I don't know, 6 microcoulombs, and then mass is equal to, I'm just spitballing, 5 times 10 to the negative 10th kilograms. So that's our mass, charge, velocity. Let's also determine, I want the force. So let's say that, okay. So let's say that the magnetic force is pointing out of the board. So it's this represents magnetic field pointing out of the board. The dot is this way. If it were into the board, it'd be like this, but we're doing out of the board. So it's pointing straight out. So what we know about orthogonal vectors, I'm going to try to draw this in 3D. So this is the negative z-axis, positive y-axis, and positive x-axis, right? I don't know if you can see that. So we know that the vector B is pointing in fully B direction. And we know that vector V is pointing fully in Y direction. So, an orthogonal vector to both of them. Okay, still recording. Sorry, the screen went dark. It's still recording. Points either up or down, but the order determines that. Since we do V first, it's going to point down. That's just the rule. We find that by using the right-hand rule. So from Y to X goes down. That's just how it goes. So this is going to be our force vector, which is equal to MA. Now, we can draw that out here. I'm just going to make some more space. And then let's give the magnetic field. Also, this is in the I-hat direction. And the magnetic field, let's say it has a magnitude of, 3 milliteslas. That's just the units of magnetic field. So this is pointing out of the board, so it's positive k-hat. Put a positive to denote that. Now, these are all strictly in one unit vector. So when we do the cross product, we're going to get a lot of zeros. A lot of stuff is going to cancel out. So we have this. We have all of our units. So now let's take a cross product. The cross product of V cross B is equal to I, J, K, 0, 0, because neither of these have an I component, J component. V has an I component, 3 times 10 to the 10th meters per second, 0, and 0, and then B has 3 milliteslas. Now, I'm going to erase this little diagram we have here. But from the diagram, we know that the direction is going to be negative. It's going to be pointing down, negative j hat. We already know that, just from inspection. So let's see what we get from the determinant, if it matches what we thought. So I, 0, K, 0, J, 3 times 10 meters per second, 0, 0, 3 milliteslas. Oh, this is negative because of linear algebra. Just a little fun fact. Negative j hat times this determinant gives us, let's calculate that real quick. 3 times, oh, I have something else. 3 times 10 to the 10th times 3 times 10 to the negative third gives us 10 to the 10th. What is this in scientific notation? Gives us 9 times 10 to the 7th meters per second Teslas in the negative j hat direction. That's just, oh, you can see it there. That is just this portion. This is this. So now, let's rewrite that. Let's start solving for acceleration so we can prove that if the vectors of v and b are already orthogonal to each other, the tangential acceleration is going to be equal to 0, and the normal acceleration is going to be equal to the total acceleration. Now, we have f of b, which is equal to m of a, ma, which is equal to q times the cross product. Let's rewrite this expression as a is equal to q over v cross b over m. Now, we have all of these values so we can plug in. Q is equal to 6 microcoulombs. V cross B is equal to 9 times 10 to the 7th meters per second Tesla in the negative j hat direction. Yes. Over 5 times 10 to a negative 10 kilograms. So Tesla is a little packet of units. There's a lot of unit work going on behind the scenes. It's just, we're just gonna avoid that because it's a little bit tedious. But the units, when you multiply all these out, give you meters per second squared. Because Teslas have a Coulomb underneath, and then these has like a Newton, and the kilogram, the Newton cancel out. Weird stuff going on. Okay, so acceleration is equal to 6 times 10 to the negative 6 times this divided by 5 times 10 to the negative 10th, which gives us 1.08 times 10 to the 12th, which is like million, I think. So like 1 million. Makes sense because particles move really quick, especially when they are under a magnetic field or in a wire. And this is the only vector direction, so it's going in the negative j hat direction, which is what we had theorized, that it was going to go in the negative j hat direction. Now, this is our acceleration. Now, I want to also add that we know that these are all perfectly orthogonal. It's like three unit vectors. So the tangential is 0 because this experiences circular motion. I'm just going to draw over all of this. This experiences circular motion, and the only force, it's the inward force, which is the normal force. So I'm going to try to show that by using the equation. I'm just going to erase this right here. So we don't need this anymore. This board is kind of bad. You put a lot of elbow grease on it. Anyways, so I'm going to rewrite the acceleration here. Is equal to 10.08 e to the 12th meters per second squared in the negative j hat direction. So first let's show that the tangential acceleration is equal to 0 because there is no direction component going this way. So this tangential acceleration is defined by the cross product of A and V divided by the magnitude of V. But wait, looking at A and V, the cross product means that you multiply each of their components. This only has components of I, so the components of J and K are 0 for velocity. And the components of I and K for acceleration are 0. So when you multiply these, when you do the dot product between them, you get 0 on top. And any 0 divided by anything is still 0. So a tangential acceleration is 0 because of this equaling 0. Now, normal acceleration is denoted by the square root of the magnitude of the acceleration squared minus the absolute value of the tangential acceleration squared. Well, we already know that tangential acceleration is 0. So this crosses out, and we're left with the square root of the magnitude squared, which is just the magnitude. So now we know that A sub n, the normal acceleration, is equal to the magnitude acceleration, which is equal to this number, just no direction vector. So that is how you compare and contrast Calc 3 and in physics. Really interesting problem. Yep. Thank you so much for your attention.